teach now at Mountainside High School, chemistry, but I taught at Forest Grove High School for many years before that, chemistry and biology. So great to have you here, and we'll go ahead and get started.
All right. So first thing we're going to do is sort of go through an overview of what the unit looks like from start to finish. So I'm going to minimize some of my windows here so it's a little easier for me to see. So I'm going to do a walkthrough so you have a sense of how everything in the unit all fits together. So we're going to start off with an opener around why do we use particular elements for generating and storing electricity, and can we predict the properties of these elements? So we did do a lot of work on the unit opener to make it a little bit more meaningful for folks to get better questions. And this is sort of the new questions that we're sort of set on. We're going to look at 3 different ways electricity can be generated through the element properties, and have students identify patterns in the properties of the periodic table and generate questions for why these patterns exist. Next, we go into what makes a nucleus stable versus unstable. This is that build an atom activity we've had in there for a while. We review subatomic particles and identify the linear pattern for stable small elements in those first 10 elements. We have an optional unit section on task on why flames are sometimes different colors, and students perform flame tests of various salts. We're working on revising that to make it a little bit more robust. And then we look at how can we predict the properties of elements by looking at graphing the data for the atomic radius, ionization energy, and electronegativity, and use those graphs to make predictions about what are the properties of elements where we don't know the ionization, atomic radius, and electronegativity. And finally, we finish off with what metals and electrolyte make the best battery, and that's our battery engineering project. So students collect data on what electrolytes, metals, and surface areas make the best batteries, and then they get a chance to design, test, and reiterate their design to make an even better battery.
All right, everybody, I'm going to talk to you a little bit about our Unit 2 objectives. So our main learning target in this unit is that we want students to use models of the atom to be able to predict the properties of elements on the periodic table. And we also want them to uncover and discover the patterns that do exist with the elements and their properties on the periodic table. And be able to use those eventually to be able to choose different materials to use in an engineering project. So that's kind of the scope of what we're hoping for students to glean by the time they get to the end. So our anchoring phenomenon, we are looking at material science basically in this unit. And so elements all have different properties that makes them useful for a variety of different applications. And so you will see in our unit opener, we're going to more broadly explore some of those applications, but then really zero in on the energy storage and transfer and generation. It's been suggested to us by our NGSS reviewer that we eventually move towards merging units 2 and 3 together. And so we thought energy would be a great bridge between what we learn about in atoms in the periodic table in this unit 2 and nuclear chemistry in the next unit. So that leads us to our central question, which is why do we use particular elements for generating and storing electricity? And what are the implications of those different materials that we use? That brings us into our NGSS main standard in Unit 2 is HSPS 1-1. And so that standard is suggesting that students should use the periodic table as a model to be able to predict the relative properties of the elements by establishing what the patterns are and explaining why those properties exist due to how the electrons are arranged in the outermost energy level. So our main cross-cutting concept is patterns. Students will look at those patterns on the periodic table a couple of different ways in the unit, at the beginning of the unit, more qualitatively, and towards the end of the unit, more quantitatively. Also, our main disciplinary core idea is the structure and properties of matter. So looking at how the structure of the atom is influencing the properties of the element. And then in this particular unit, I would say that students are probably using models more than they are necessarily developing models, although they will be developing a periodic table on their own at the very beginning as part of the unit opener. That brings us into our next slide. which is 3D learning. Oh, one back.
Why did that? Oh,
there we
sorry.
go. So those aren't the only practices, cross-cutting concepts, and disciplinary core ideas in this unit, because of course we're engaging in other activities as well. So students will be analyzing and interpreting data in the Build an Atom lab. They will be constructing explanations and in the lab, and also designing solutions in the engineering project. They also will be asking questions in the unit opener and defining problems when they get to the engineering project. Cross-cutting concepts besides patterns are also the influence of science, engineering, and technology on society and the natural world. I think a lot of times our students look around and, they live in a world that has been, engineered and manufactured, where everything is working pretty well all around them, but they really don't take a lot of time to stop and think about what amount of thought and research went into choosing all of the different materials that make up all of the things that we use on an everyday basis. And then last, our disciplinary core ideas besides structure and properties of matter. We'll also be looking at defining and delimiting engineering problems, defining possible solutions to those problems, again, in our engineering project, and optimizing the design solution. So in the engineering project, depending on how quickly students are able to build their design, they might also have time to iterate that design several times as well. All right, that brings us into our unit opener. So this was our big overhaul in this particular unit. And so what we did is that not only did we kind of change the unit phenomenon to better align with being able to eventually merge units 2 and 3 together, but we also wanted to include the create a table activity into this unit opener. But in order to do that, we had to make some changes to that create a table activity. So we actually completely made new cards. And so again, those cards, I think, are better than any of the ones that we've ever previously used. So we're excited to share those with you tonight. So the essential question in the unit opener is, why do we use particular elements for generating and storing electricity? And can we predict the properties of those elements then? The phenomenon is that elements all have different properties, and that those properties can be predicted, and that makes them useful for a variety of applications. The objectives with the create a table part of the unit opener is that students are going to use cards to build their own periodic table based on the physical and chemical properties of the elements, just like Mendeleev did. They're going to find patterns in the properties of the elements within the group first, and then within a period. And then students will use those patterns to make a prediction of a missing element. So there is still a missing element, as there was before. And then students will use the information not only from the brief opener, which also connects back to what they learned in physics, but also from the activity, because students always have really great questions after they've done this initial activity. And so we wanted to capitalize on that and include that as a way for them to populate the driving question board. Okay, so now we're going to go to the unit, the teacher unit. Oh, 2 opener slides. Great. Okay. And so on this first slide, again, we're just reiterating what those essential questions are for the unit, and reiterating that idea that elements all have different properties which make them useful for a variety of applications. I think this is a great opportunity for students to be able to get a little bit of an introduction to what materials science is. And so on our next slide, we have a short video to introduce us to that idea of that profession and career.
Do you want me to try to play that video, Jamie, or do you want to just
why don't you try to play it? It's really short. So.
Okay. I'm going to stop sharing for a minute just to make sure that when I share my screen again, that I have it shared for sound.
Sounds great.
Okay. And please.
What springs to mind? How about a complicated system of parts, working efficiently to produce the best possible performance, as in a Formula 1 engine?
Or do you think about the manipulation of energy to produce sustainable motion, like in a wind turbine?
Then again, you might think about the structural challenges involved with supporting 8 football pitches of glass, such as in the Shard.
Regardless of what you think of, an underpinning factor involved in all of these engineering challenges is the materials used.
Material science and engineering is an interdisciplinary field that uses physics and chemistry with elements of biology. Bridging the gap between science and engineering, material science is used to understand the structure and properties of materials and how we can best exploit them.
It is a science that is truly used for real-world applications. It covers many areas, such as polymers, ceramics, corrosion, and metallurgy. For example,
metallurgy is the study of metals which are formed by atoms arranged in a regular crystal lattice, joined together by a metallic bond. This type of bonding consists of a sea of free electrons which give rise to the metal's characteristic properties. By manipulating the structure of the metals and alloys, it is possible to improve their properties.
This concept is not a new one. For example, blacksmiths from the Middle Ages knew that a metal's properties could be improved by working it with a hammer.
Through deeper understanding of these principles, it is possible to make our metals stronger, tougher, lighter, and more reliable. Industry is constantly developing new alloys tailored for their applications, from aerospace to sports equipment.
Material science and engineering is at the forefront of many technologies, including renewable energy, nanoscience, and spaceflight. It also has an impact on our everyday lives. Products and technologies we take for granted have been made possible through the study and application of materials.
There are still many intriguing and exciting problems to solve. If you are interested in learning more about material science, watch our video on material selection.
Alternatively, if you need no more convincing and you've decided materials is for you, watch our video Starting a Career in Materials.
All right.
Okay, thank you. So I love that video because again,
If
it is
someone were
brief,
to ask
but-
you,
it
Sorry.
does give a good introduction to materials, and it does help students to realize that everything around them that they use, the materials for that object or whatever it is that they're using, they were chosen for specific reasons. And around us, we have a lot of industries like Boeing and Nike and Intel that are very driven by material science research, and that is an opportunity for students to have a future career here in the Pacific Northwest if they choose to stay here. So, again, always trying to think about making those career connections. All right, let's go on to the next slide.
Whoops, there we go.
So on this slide, again, we're trying to start more generally about what are some elements that students would be familiar with in different products that they use on an everyday basis. So we've got some helium in the balloons, we've got aluminum and foil that we would use in our kitchen, copper in wires. Everybody's seeing all of the advertisements for the new iPhones that they have titanium in them, lithium in the batteries that power our phones, and then of course silicon in processor chips. So I think we'll try to do a little waterfall here. So it says, what properties do these substances have that make them useful in society? Use the picture to help you with ideas. So for all of you out there that can access a keyboard and are able to type in the chat, I would love for you to choose one of these substances here or come up with your own and say why that substance is a good choice for that product. And so let's just type it in the chat, but let's not hit enter yet. And maybe give me a thumbs up when you have typed your answer in the chat.
Put my personal thumbs up, but
That works too. I
what
was
you're
going to say,
looking for
if you haven't used in Zoom
is
in a while or whatever, yeah, it's under reactions now. I do remember
There we go.
mid-year in CDL, they moved it from where it used to be to where it is now.
Oops. I was trying to get into the thing and then I ended up going back into the slides in the wrong place. That's what I get for
Okay.
trying to participate.
Well, I think most of my thumbs up have kind of come away or come on and then they've kind of gone away. So I'm going to hope that that means that we're done typing. So I'm going to count down from 3. And when I get to 1, everybody hit enter. 3, 2, 1. Let's see what we've got for responses here. Good, okay. The balloons float, great. Lithium for batteries, good. Silicon, inexpensive and abundant. Great, we're getting quite a variety of different answers here. And so that's hopefully what we're gonna get from students as well. And again, it's just to get them thinking about that they do already know something about the properties of elements because they do interact with different elements on an everyday basis. Okay, now we are gonna go on to our next slide. So in the physics curriculum, when they are working towards the end of the year and they're learning about energy generation and how the different ways of generating electricity, they learn about these different ways: wind power, tidal power, hydropower, nuclear power, and solar power. And part of their learning is them watching videos on these different ways to generate electricity. So I have linked the videos for wind power, tidal power, hydro, and nuclear. So if you kind of hover over that part of the slide, it should take you to the place where you can watch the video there. But, you know, I'm going to assume that most of us are not currently teaching physics or maybe haven't taught physics. So what I'd like to do is give you a few minutes just to explore those videos, because part of what we're trying to bring forward in this part of the unit opener is thinking about not only having students explain how do these ways create electricity, but also what we're really focused on is what do they have in common. So I'm going to give you a few minutes to explore those videos, and when you're ready to move on, give me a thumbs up. And Andrea, I'm not quite sure what's happening, but like, I don't know, it has some places on my screen that looks like the slide is redacted.
Does it look better now?
Looks like there's one at the bottom and then one at the top. I don't know what's causing that. The one at the bottom's gone now.
Yeah, those are like the Zoom screens. It has decided that you cannot see where the Zoom controls are.
Oh, okay.
So I'm going to log in with my other computer so that I can see things like the chat without getting on top of any of the slides.
Okay.
I'm going to move this Zoom thing down to the bottom so I'm covering up less stuff. And as soon as I get my, oh, you got it. Thanks, Jerry.
Mm-hmm. Maybe about, oops, I would like each person to share about how one of these ways that you explored made electricity. And then after each person has shared, what I would like you to do is talk about what is the similarity, right? What do all of these ways of generating electricity have in common? All right, here we go.
Right, and then since you're putting us into breakout rooms for this conversation, I will pause the recording while people are in breakout rooms.
Okay, everybody, I appreciate you chatting with one another for a few minutes. Hopefully we have figured out at this point, I'm gonna go on to our next slide, but the thing that all of these ways of generating electricity have in common is that they're all hooked up to a generator, right? And so some of these are screenshots from the actual videos themselves, but with the wind energy, we have a propeller, right? And that propeller is connected to our generator. Hold on one second, I need to. There we go. When we have hydroelectric, obviously the water is moving through the dam. So as it's moving through the dam, then it's going to turn a propeller, just like the propeller that's very similar to the outside of the wind turbine. And that is also connected to a generator. And then even if we introduce coal into the mix along with nuclear, coal and nuclear are both used in a similar way because they're used to heat up water. That water creates steam, and then the steam turns the turbine, and that is connected to a generator. So again, trying to look for that similarity of how are these all in common. They all are hooked up to a generator. That it's that generator that's actually taking the wind energy, the water, the steam, and turning that into actual electricity for our use. So
and I just want to say, so Jim, before you move on, one of the conversations that I heard in one of the breakout rooms, and I don't know if other people are in this same boat, is that some school districts are not doing physics first, they're doing physics for juniors. And so if you have a group of people, we talked about it in this in council, if you have students who have not been exposed to those videos, one of the suggestions we talked about in council is that you break up, you jigsaw them. So you have a group of 4 people and each person in the group watches a video, kind of like what you just did there. And then they can still have that conversation and you can just say, you'll get back to this when you get to physics next year, so that it's not, you can still do the activity even if you haven't experienced this before. Sorry to interrupt, Jemma, you go ahead.
Nope, you're totally fine. Yes, we did talk about that. And just even at schools where physics is being done, maybe for whatever reason they're not doing that unit or, whatever, trying to make it flexible. So that brings us into, now that we know that they all use a generator, we want students to think about or remember, how does that generator work? And so again, in physics, they use this very simple FET. So feel free to click on the link here just so that you can experiment with it yourself. But the thing that we want students to do inside of this FET is that we want them to turn on the voltmeter. And then we want them to take the magnet and move it inside the coil of the wire, right? And so once they've done that, they can either flip the magnet back and forth or they can manually move the magnet back and forth. But what we want to know here is that when we move that magnet in this coil, what happens to the voltage? That's really what we want to be looking for. So take a moment to just play with the FET there. And then why don't we, I lost my chat again. Why don't we, once we've taken a moment to play with that, why don't you post in the chat, what did you notice happen to the voltage as you were moving the magnet in and out of the coil?
And I dropped the link in the chat for the FET in case you don't have, if you can't get the slide link to work. Jermaine, did you want them to waterfall again or just drop it in the chat whenever they get their notice?
Just drop it in the chat whenever you've had a chance. Good. Yeah, great. Yes, if you move it fast, it blinks. Good. Move it fast enough and it won't blink anymore. Okay, great. Great observations. Yeah.
It's funny, I've always moved it in and out. I've never moved it up and down, and this time moving it up and down all makes it work.
Yeah. Well, so essentially what you all have just experimented with, if you've just experimented with how the, I guess we would call that mechanical energy is being turned into electrical energy. So the turbine, it can work one of two ways, but the turbine is usually either attached to the magnet and that moves the magnet within the coil, or sometimes the coil, like the magnet can be fixed and the coil can be moved by the turbine around the magnet. But either way, what we can see is that when we have movement of a magnetic field around this coil, that we're going to get some electricity, right? And so then it's easier for students to see that because it's hooked up to this light bulb. So what we want to think about now then, and what we want students, this is where we're kind of really starting the unit opener about, what do we notice about the substances that are being used here? And what do we wonder about the properties? So I know I've kind of skipped over some parts of the unit opener for the students, but if I go back to our Unit 2 overview slides, there is a student document for this. And so if you click on that link, it will open you up. So I kind of skipped over having anybody write anything when we were going through these initial parts. But of course, if you were doing it with students, you would want them to stop each time and take a moment to jot down their thoughts. And so instead of writing it in this document, you're certainly welcome to make a copy of this document if you want. But instead of writing it in this document, what do you think students would notice about the substances being used here to generate the electricity in the Faraday's law FET? Or I'm going to have you guys post one or the other. Or what do you wonder about the properties that allows them to generate electricity? So this time I am going to have you guys waterfall. So again, pick one question or the other to answer. What do you notice about the substances being used here? Or what do you wonder about their properties? Now you guys are all teachers, so again, kind of put yourself in the mindset of the students and try to think about what you think students would say when you're posting. So we're going to type out our response, and then in about a minute, I'll have everybody hit enter. Okay, about 15 seconds to wrap up your response. Okay, everybody hit enter. Let's waterfall. Okay, great. Got a question about electron flow there. Yes, there is an option in the FET where you can use more coils or less coils. So good. We've got some physical properties there that they're solid. Good. We've got one substance that's magnetic and one that's not, but yet they seem to be interacting with one another. What is the coil made of? We also had another observation or another noticing that they're both metals, right? And so in the video, it was talking about that we're constantly manipulating metals to think about how we can use them in society. Obviously, one of them is conducting electricity. That's how we're getting the voltage. Great. Okay. All right, so back over to my unit opener slides now. So now that we have noticed and wondered a little bit about that generator, now we're going to move on to a different type of energy. So solar, what did Kermit used to say? One of these things is not like the other. Solar is a little bit different than the other forms of energy because it does not actually have a generator like the other forms of energy do. It generates electricity in a little bit different way. So most students would be kind of familiar with seeing the photovoltaic panels that are oftentimes now on people's homes or businesses or out in fields. And so again, I think I have linked this to a video about solar panels. So again, if you feel like your students are not very familiar with that form of energy, it would probably be a good idea to stop maybe as a class and watch that. But I will just give a quick overview. Over here on the right-hand side, we are seeing something that's very similar to what they saw in the FET. So in a photovoltaic cell, we have a layer of silicon, right? And then we have our sunlight coming in. And so as the sunlight enters, it knocks electrons loose from the silicon atoms that are in the middle layer there. And then the solar panel has a negative layer, and that's on the top, that's being pictured by the brown. And it also has a positive layer, and that is being pictured by the gold here. And then it's also telling us that we have some metal strips again, and that those are conductive. And so that is causing, again, electrons to flow through this panel, and eventually it's being hooked up over here to our light bulb. So as the electrons are going through our light bulb, and then they're returning back to the positive end. So a little bit different, not a generator in this particular case, but we're still using a material. And in this case, we're taking the sun's light, we're using it to create chemical energy, which is eventually going to become electricity here. So again, we would want to stop and think about what do we notice about the substances being used here, and how might they be similar to maybe some things that we saw earlier in the unit opener? And what do we wonder about the properties that allow them to generate electricity? So I'm going to pause for a minute. Again, you guys are going to write either something that you notice or something that you wonder. We're going to hold that, and in 1 minute, we'll post our responses again. Okay, everybody, I'm going to count down from 3 again. When I get to 1, everybody hit enter. 3, 2, 1. See if I can get back down to, I scrolled up too far here. Let's see. Good. I wonder how the sunlight's able to move the electrons. The light bulb's part of the circuit. Great. How much electricity? Metals being used again. Great. Yep. Semi-metal. So we talked about that earlier when we were doing our unit opener, although we saw it in a processor chip earlier. Why are the panels blue? Okay. I think this is somebody responding with the boron opaque. Okay. All right, good. So again, trying to think about material science, like why do we pick the things that we do to work in the solar panel? How does that help them efficiently generate electricity? Okay, that brings us to batteries. So we've been talking a lot about how energy is created or how it's generated, but we haven't really talked much about how batteries or how energy can be stored. And so we're going to take a moment to look at a couple of different batteries here. So we have a lithium ion battery being pictured on the left-hand side. And then on the right-hand side, we have a dry cell battery. So again, you would go through the same process with students. Like, what do you notice about the substances that are being used in these two different types of batteries? What do you wonder about their properties that allows them to take this chemical energy and turn it into electricity, right? Allows us to store the energy until we're ready to actually use it. So in the essence of time, I'm not going to have us notice and wonder about this again, but certainly you would want to pause and have students do that one more time before we move into the next part of the activity. And so Andrea, do you want me to stop so you can start screen sharing?
That sounds great.
Okay.
And I will start sharing with the show, but I need to get out of this to get back to the correct place that I want to be. All right. So here on the Unit 2, once we get through that, here's the virtual slideshows. We have students take these cards, and I'm going to go into the slideshow, and we have them sort out these these cards into a periodic table. Now, what we're going to do here online is a slightly different version of the activity than what you would want to do in person. So I'll have you go through and do it with your group, and then we'll talk about what some of the differences would be and how those relate back to what Jomei showed on the student handout. And the reason we've made these changes is that some of the things are a little bit hard to follow in a virtual environment, but are easier to follow if you're doing them in person. So I'm just going to kind of walk through what you're doing, and then I'm going to have you go into breakout rooms and sort of experience what you're doing. So let me share this quickly, the Jamboard. Not a Jamboard, it's a slideshow. So we've got this activity, and you're going to start off with, you've got these 4 elements that you're going to have in, that you're going to be able to play around with. And what you're going to do with that is you're basically going to take them. I'm going to escape out of the slideshow because you need to not be in slideshow mode to move them around. So you're going to move them around, and you're going to first arrange them in a vertical column from lowest to highest number. And if they're too big, you can shrink them down or make them bigger, but make the cards roughly all the same size. And then once you've done that, you're going to do the second thing of look for 3 patterns that show up once the elements are in this order. Now, once you've done that, if you're doing this in person, you're going to then try to group the cards based on the patterns that you noticed. And you would do this with the whole deck, but we can't fit the whole deck on the slides. But in person, you can cut out the cards and do the whole deck this way. Now, we've added this thing about organizing a specific 8 elements in an order so that you can do the whole group. In person, you don't do that, but we'll do that here because it's easier to do. And then you're going to organize the different groups themselves. So that's what you're going to do as a group. We're going to put you into breakout rooms to play around with this a little bit, and then we'll take you back and have you look at what it looks like on the student handout. Any questions before we send you back into breakout rooms for a few minutes to play around with the slides? Okay. I'm going to go ahead and pause the recording. I'm going to go ahead and resume the recording. Now, the intention behind that was to have you guys just kind of experience, play with the cards a little bit.
If I push the button, will you grab the door?
Hang on one second. All right, let's get you guys a chance to play with that a little bit and see what's going on. What I want to do now is to sort of share what is the students are actually doing. So in general, what we do in a classroom is we start off with this. This is the second part of the student handout. And so we would start off with having them take those first 4 elements. You give them a whole stack of the cards and you say, find these elements. First, start off with magnesium and then talk about what's on that specific card. Then you find all the elements that are in that first column, just like you did on that first slide. And then you once again look for what are the patterns you see with that column of the magnesium, beryllium, calcium, etc. Now, instead of having them group a small subset, we have them group the rest of the elements. The reason we didn't do that virtually is there's just too many and you can't see what's going on. So you would organize and group the rest of the elements. When students get stuck, I have found that telling them to make groups and then keep those groups and organize those groups generally gets students unstuck, because I know sometimes they want to reorganize multiple times. And then once you've got them, they've gone through one column, then two, they've organized all the cards into 8 groups. And then they've taken their 8 groups and they've organized those 8 groups into, like, from left to right, this should be my first group, my second group, my third group. Then you organize within those groups, then they have a whole table and they can analyze and find the missing element. So that's what they're having them do as they go through this worksheet. So it's a little, and then once they've done it, they have these 2 missing elements that allow them to then start making predictions. And in my experience, they generally 2 things happen from that. And that is, they can usually get all of the pieces of the element. And if they're stuck with the blank pieces, you can say, well, what do you think would go in the left corner based on what's, in this column and in this row? And piece by piece, they can make it through. Jermaine, did you want to add anything to that as we think about going back into the driving question board related to this? I'm not hearing you, Jermaine. Did we mute you by accident?
I might have muted myself. I was just going to say students come out of that activity with a lot of great questions about, like, why are the atoms getting bigger top to bottom? Why are they getting smaller left to right? Why are they getting more reactive or less reactive going this way or that way? And that's why we really felt strongly that that needed to be included as part of the unit opener, because they really, after this activity, are asking a lot of those questions that they are going to discover the answers to as they dig further into the patterns later on. The other thing I will say about the new cards, some updates to the new cards. So the reason that we made new cards was that, first of all, we wanted to add in a whole new period of elements to the bottom. And some of those elements are radioactive. And so that was, needed in order to tie kind of these units 2 and 3 together. So we really needed those radioactive elements that are coming in that next period. Also, if you ever use the old Living by Chemistry cards, it was very difficult for students to discern that what the state of matter was through the symbols, because there was a color around the outside of the circle to indicate whether it was a solid or liquid or gas. And that was very difficult for students to be able to tell. So in the new cards, it's very clear. If it's a solid, it's a cube. If it's a gas, it's a balloon. If it's a liquid, it's a droplet. And then also we talked about in the council that we were worried about giving the wrong impression that the elements were indeed these colors that we've colored the spheres with. So, within the balloon, the droplet and the cube is the actual color of the element also. So, again, trying to make sure that we're as accurate as possible. We didn't want to remove the colors because it does aid in students being able to assemble the entire periodic table very quickly or very easily. So that's some of the updates that were made to the cards, just so that I just wanted to pull up different.
Sorry, I just wanted to pull up the full set of cards so that you guys could see them, so that you could see what Jermaine was talking about the cube and the balloon. And there's only one liquid, so I don't know where bromine is down
there.
There
it is, right there.
It is. Yeah, there it is. And then our liquid, so that you can kind of get that and see that a little bit better. And I know that when we were doing this, there'll still be like a gray scale. If you cannot manage to get them color printed, there's still enough other information that allows them to put them into categories fairly easily.
Yes. Okay, before we do our driving question board, I think we should take a quick brain break or stretch break. So let's just take 5 minutes, take care of your needs, and we'll meet you back here.
All right, and I will pause the recording while we're doing that. Opener. Oh, thank you. When we do the unit opener, we're going to go ahead and once again, we're going into that periodic table activity, and we're going to have them go through and spread the cards out, find magnesium, share what's listed on the card, talk about the background of what happened with Mendeleev. Then they find those 4 cards of that sort that we did a minute ago, where we just go from smallest to biggest. That's what we have students do with the actual cards. Then we find a way to do the rest of the cards in the table by grouping them into groups and then organizing those groups and adding the cards to the bottom of the table. So that's how I usually do it. So in this part 2, they're going to make 8 groups and then figure out how do I put those groups from 1 to 8 and how would it organize within each one of those groups. That usually gets folks to the periodic table with the missing cards. We've added these 8 cards, some of which are radioactive, and they can talk about how those may or may not relate to generating electricity. That'll bring up more questions. And that puts us to our driving question board. Jo May, you want to talk about that?
Yeah, so as we get ready we're going to go back into our breakout rooms one more time to make some questions for our driving question board. But what we really want to think about is that early on in this lesson, we thought about different ways to create electricity, and we thought about the substances that we use in order to create that electricity. And so now we're trying to bring that together with questions that we also had about the properties and the patterns that we saw with the elements on the periodic table. And so ultimately, when we go into our breakout room, when we're trying to write some driving questions for the unit, we want to think about what do we as scientists and engineers need to know or investigate or model in order to understand why we pick particular elements for generating and storing electricity. So you and your group members are going to just verbally brainstorm some questions, several different questions, right? Then as a group, what I'd like you to do is pick 1 or 2 of your best questions, or maybe there's some similar questions there that you can combine into one question. And then we will need at least one person from the group to post the 1 or 2 questions that your group wants to share in our Jamboard. So I'm going to copy that link and I'm going to put it into the chat right now. Okay, so when you post that sticky note for your group, just make sure you put your breakout room number, so 1 through 8, and then put what your question is. If your group comes up with more than one question, then go ahead and post 2 sticky notes. And then I will stay out here and try and do a little bit of organizing of our questions, and then we can come back together and see what groups we've got. All right, so let's get the breakout rooms ready.
I'm going to stop sharing.
Let me open those rooms back up now.
And if you lost connection and had to reconnect back in, if you just want to let me know what breakout room you were in so that I can put you back in this with the same folks, just drop that in chat. So Christina, if you want to tell me where you were at, I can put you in the right room.
Yeah.
Christina, what room are you in so I can put you in the right spot?
Atomic radius, because that determines the other properties. And then we're also looking at ionization energy and electronegativity, as that's going to control the chemical reactivity of the metals and the nonmetals. So our essential question here is, how can we predict the properties of elements? And the phenomenon is that Mendeleev predicts the properties of elements that had yet to be discovered. And that was based on their placement on the periodic table. So, although we might not be super familiar with all of the elements on the periodic table, we should be able to use the patterns that we find on the periodic table to make predictions about how those elements might behave and what their properties are, and whether or not they might be good fits for, again, different purposes in society. So they are using models here. They are developing models because in this case, they are doing the graphing of the actual ionization energy, electronegativity, and atomic radius. They're looking for patterns within those. So again, they've seen those patterns qualitatively earlier on, but we're revisiting those patterns again. And again, there are missing elements in this data set where they are now coming back and quantitatively making a prediction for what that element's ionization energy, what its reactivity or electronegativity, and what its atomic radius is going to be. So again, revisiting that, hitting it again a little bit more in depth this time so that we understand why the elements have either higher or lower reactivity levels and why that might make them a good fit for a particular product or not. In this particular task set, they are looking for an element that's relatively non-reactive because they are trying to look for something that they want to put into a straw, into an alloy to make it stronger. So we don't want a particularly reactive element in this case. We want something that's more non-reactive, kind of like our aluminum foil. And then, of course, as we've been focused on in most of the task sets in this unit, looking at the structure and the properties of matter. Oops. Okay, so students make a wild guess about the correct element that they need to add to their steel to make it more rigid. Again, it's supposed to be in a straw. They're going to learn about the properties and relate it back to the properties that they identified at Create a Table. So again, returning to those initial ideas, they are going to hypothesize about how the property depends on the atomic number. Then they're going to graph their data, graph their property, determine their pattern. But not every group graphs the same data. So they go through a process where they jigsaw the data as we do in all the patterns labs. And then they have to go through a process of sharing those patterns and those trends out with each other. So although they're not graphing every single property, as they go through the jigsaw, they learn about all of the different properties and the patterns of those properties, top to bottom, right? Top to bottom and left to right. So after they're done with the jigsaw, then everybody has learned about all of the different properties that are present in these three sets of, I guess I would call them physical and chemical properties. And then at the end, they come together to use those patterns to make a data-informed prediction. They do have choices of the elements, so they are not just choosing from any element on the periodic table. I think it starts them off with 3 or 4 choices of elements that might be. Yeah, I was going to say Andrea wrote that part. So she knows, but three choices. So, that again confines the playing field a little bit. So makes it a little bit easier on ramp for students. All right, so the key takeaways here are, what are the patterns on the periodic table that we see? Well, again, like I said earlier, it all starts with atomic radius. So atomic radius increases from top to bottom, and that's due to more valence shells of electrons being added to the size of the element, and that's causing it to enlarge. Going from left to right, I would say out of all the patterns, this is the most difficult one to understand, because students are like, well, but it's gaining electrons, but they're in the same valence shell. But at the same time, they're also, the nuclei are gaining in protons, and that's causing the attraction between the nucleus and the valence shell to become stronger. And so that's actually pulling the radius inward, right, and causing the size of the atom to decrease as we're going to left to right. So I definitely know when I do this activity with my students, I definitely tend to assign, that particular property and pattern to students that I know are going to be able to grapple with that little bit more difficult concept more easily maybe than some other groups. Then we have ionization energy and electronegativity. Those track together. And so they definitely increase from left to right. And again, it goes back to atomic radius. There's more protons in the nucleus, right? That creates a stronger attraction, right? And that is going to allow either non-metals to more easily attract more electrons to their outer shell. or if they're metals, it's going to allow them to more easily give away those electrons or release those electrons to create a full outer shell. And then those patterns as well decrease from top to bottom. And again, the valence shell goes back to atomic radius. So the valence shell is further away from the nucleus. And so those outer electrons are less attracted to the nucleus. That is going to make them easier to be removed or taken away, causing the metals to be more reactive. And it's going to be more difficult for the non-metals then to attract electrons to that outer shell to fill it in order to be reactive. So, two different properties, but very much measuring the same thing as far as reactivity is concerned. And I know that a lot of times we have reverted to looking at electronegativity rather than ionization energy in many instances, just because ionization energy very quickly gets complicated with first ionization energy, second, third, etc. And so sometimes we just go with electronegativity because there's just one value for each element. All right, last, that brings us into our battery engineering. This is like our culminating project of this particular unit. And so in this case, what we are trying to do as students is design a battery for an emergency situation. And so they need to know what metals and electrolyte are going to make for the best battery. And they are going to test them, different types of batteries that they're going to make from different metal combinations and different electrolytes. So again, this will be in the format of a jigsaw. Different groups will test either metal combinations, electrolytes, different things that would affect the performance of our battery. So the practices that we're focusing on here will be defining problems and then making an actual design and evaluating the solution of their design. They are, taking chemical energy and transforming it into electrical energy. So cross-cutting concept is energy and matter. And we're focused still on that same disciplinary core idea that the structure of the atoms has to do with the properties of the matter. And so why certain metals might work in our battery paired together better than others might. Okay, so the kind of process of the battery engineering project, which happens over several days, is that on the first day, students explore just kind of some basic information about circuitry. They make a little mini LED flashlight just to get them thinking about the idea that we have to have a complete circuit in order to light up our LED. Then the next phase is that they move into testing, like certain groups will test different electrolytes, other groups will test different metal combinations, and then surface area also to see how that is affecting the current of the battery. And then they will share that information out with each other. Now, when they share this information out, it's a little bit more informative because it's supposed to help them decide in their groups what they are going to build their battery out of. So they go ahead and collaborate on that. And then at that point, they're ready to design their own battery, right? They need to have multiple cells in their battery though. So first we kind of help them build that single cell. And what I encourage students to do is kind of do a cost analysis of their single cell, because there is a budget that they are supposed to stay within. And so if they built their single cell and are already quickly approaching their budget, then they're going to have to figure out how to scale their battery down to come closer to the budget. So then they hook their multiple cells up together. And then once they've got their multiple cells working, we attach the LED. They usually go into a dark place so that they can kind of see the light output from the LED. And then it concludes with them thinking about the pros and the cons of their design. Again, some students, depending on the design, might finish their design and get their LED to light up very quickly. In that case, it's fun for them because they get to iterate their design. I encourage them to make it better, to make it smaller, because hey, that's what we're doing in society, right? We never have a 1.0 of anything. We always have a 2.0 and a 3.0 because that's what material scientists are constantly trying to do. Make it lighter, make it faster, make it more efficient. And so
I just want to add something.
Students get a chance to do
about
that.
the building and the testing. When I do the building and the testing, I get a little silly with it. And so I always build an obstacle course in the back of the room to simulate what it's like to go through an emergency situation. And going through the obstacle course in the back of the room becomes this big challenge, and everyone's like cheering each other on and sad if they miss it. And it makes people more inclined to want to redesign and reevaluate and do pros and cons because they're thinking about how do I get through this pile of broken chairs and things in the back of the room. Anyway,
Yes, so like my LED lights up, but if I drop my flashlight on the ground, everything falls apart and now I'm sitting here in the darkness.
Yeah, absolutely. All right, so at this point in time, take a few minutes to fill out the PMSP exit ticket. If you haven't recorded your attendance, I'm dropping the attendance in the chat as well. And we can stick around here for a few minutes to answer any remaining questions you might have. I'll go ahead and stop the recording because I don't think there's any reason for everyone to get that.